let's have a good one. This could be, I don't know, this might be the one I submit for Teacher of the Year, but we'll see how things go. All right, I'm hoping. Is there? I think there is. So.
Those are witty ones, not you've already won it.
Yeah, that was like $25,000. All right. Yeah, there's nothing. I'd apply, but I don't even. All right. So homework. Let's take a look at that. So any questions on those? Packet.
Oh, I need it.
Okay.
Should have been hard.
Wow, Joe, you didn't even.
It's not the front page, it's the next page. Nothing? Not, oh, come on.
I said 57. Was it really? Okay.
No, in the packet.
Oh,
It was pretty easy, right? Yeah. Now, so let's, all right, let's go through a few answers. Okay. So your answer to 11 was 12 for 12, 8A, 8, 4, 4. Okay. Now let's talk about. Okay, so let's just do one here. Now we gotta be a little careful. We say was it really this easy? But so we're talking about area. Yesterday was, well, actually Friday with the video was the introduction of this integral symbol, which basically means area, and it means area between the curve and the x-axis. And we have really only one way of exactly calculating area right now, and that's with our old geometric formula. So triangles, trapezoids, squares, rectangles, half circles, and those kind of things. And the reason we say half circles is a full circle would be a function. So typically it's going to be half circles or quarter circles, something like that. Okay, those triangles. Those are the kinds of things we can do the area. Now, other kinds of shapes, that's what we're going to get into. Actually, we're going to kind of start that process today, is how do we find like the area under a parabola or under the sine curve or those things that don't make geometric shapes. Surely those have an exact area. How can we find that exact area? That's kind of the goal. That's where we're headed with this. Now, so we take one like 15. So if we graph 2x plus 5 and we go from 0 to 2, okay, we're talking about that integral describes that piece of area. Well, that's a trapezoid. The area of a trapezoid is 1/2. This would be 5 right here. So this side would be 5. This side, if you put in a 2, would be 9. So it's 1/2. The bases, which are those two parallel sides. Now, in calculus, almost every trapezoid we deal with is going to be a trapezoid tipped up on its edge. So the parallel bases are actually running up and down. And then what's the height? That'd be this down here, which is 2. So those cancel. 5 plus 9, 14.
What's the answer to 13?
13, the answer was 8. 8. Because that would just be y equals x. It would be a 4 by 4 triangle. So 4 times 4 is 16. Half of that is 8. Right? Now, when you take a look at this, so like 17. So on 17, you've got to be able to, without a calculator now, and I don't know how many used a calculator here, you've got to be able to graph these without a calculator. Our next quiz will be no calculator, so there'll probably be some of these where we have to draw, or maybe a picture will be given for you, but if you have to draw, you got to know that that's a V graph flipped upside down, shifted up 1, which also means since the slope is 1 on those, it's going to cross here and here. So the area from -1 to 1, they could have made that harder by not just doing -1 to 1, right? They could have made you add on some of this negative area, like if they went -1 to 2, right? Then you'd have had another piece of triangle over here that would have had some negative area that you would have had to add on. But for this case, it's just this piece of area, which is a triangle. It's 2 by 1. So 2 times 1, half of that is 1. So for 17, should add 1, right? 18 is the same thing, except it shifted up A. So now instead of being 1 tall, it's A, and then it goes from -A to A. So now you'd have an area that's 2A across times A tall times a half. So that'd be A squared. So the answer to number 18 is A squared. And then yesterday we talked about 19. What kind of a picture is that? No. That's a half circle. From -3 to 3, you need to be able to just look at that equation and know that that's a half circle at the origin radius 3. And it's the top half. Okay, and so it's that. And so that's just pi r squared, which would be 9 pi, and then it's half that. Okay, now what is this then? Same thing, except it goes from negative r to r. It would be a circle, radius r. Well, that's just pi r squared, and then half that. Right? Yes?
For like 19, would it change anything if instead of 3 to negative 4 to negative 4?
Sure. Now, let's read that. I don't like how you read that 3 to negative 3. Always start with the bottom. So negative 3 to 3 is how we're going to say that. So negative 3 to 3, yeah, I would definitely change it because now you would have, well, I can't think of a time we'd ever ask that. Because from negative 4 to here, there is no area.
Yeah, that's what I was wondering if it would change.
And to there,
Oh, okay.
so
Wait, how did you get
it's not even defined at those places. So the problem would, I just can't think of a time that would even be an issue. So we won't worry about that right now. Okay? Because when we get into where we actually have some formulas we can use, and then we started trying to plug in a 4 and a negative 4, we'd run into trouble because it would be undefined, and so we'd have to be careful of that. Okay? All right. Now, what I do, okay, any other questions on that? What's that? Well, because it's half. It's just half.
Oh, okay.
It's just half. So it's half circle, so we have to divide.
How do you know by looking at that it's half?
Well, you just have to recognize it. Here's why it is, though. If you get y equals square root 9 minus x squared, if we square both sides, we get this. If we add x squared over to that side, it's x squared plus y squared equals 9. And that's just the area of a circle. We just know that from memory. Second day of class, I think we talked about this because we were doing piecewise functions. Remember, we said you got to know the area of a circle is this. So anytime you solve that, it's always going to be this radius squared minus the x squared, then the square root of that. So anytime it looks like that, that's half circle. So yes, so that's just kind of a recognition thing that's what it is. Okay? Now, I want to show you something on the calculator here in a minute. So let's talk about number 6. I told you to skip 6 and 7, right? Now this is something, we're foreshadowing something that's going to come later. But when we write f of y, that's the same as what? X, right? Just like f of x is the same as y, right? So this is x equals y minus 2 squared. Now, the reason we write something like that is a sideways parabola. So what you have is a sideways parabola here. Okay, now we only have one part of it. We actually have the bottom half of it, right? Now, it is possible to think of this area in 2 ways. We can think of this area as the blue area, meaning this area between the curve and the x-axis. That's how we normally think of area. The problem is, if we're going to think of it that way, we have to write it as an f of x kind of equation. We have to solve for y, right? So how would this look solved for y? Well, we would square root both sides, right? Now, would it be the positive or minus square root? No, because this is a sideways parabola. Which part of the parabola do we have? We have the bottom half of the parabola. So it's actually the negative. Then we add 2. So negative root x plus 2 would equal y, right? So it's kind of like the root x function, right? And then flipped, and then shifted up 2, right? If you look at it, then that kind of makes sense, okay? Now, what would that integral be then? What would the blue area be if I wrote it as an integral? 0 to 4, negative root x plus 2 dx, right? That would be this blue area. But it's also possible to think of this area as this area, right? Which is the area under the curve to the y-axis, right? We defined our integral to be the area between the curve and the x-axis. So normal functions, normal area, that's how we do it. But it will sometimes be to our advantage later on. So it's not a big deal right now. But it will be to our advantage later on to think of this as an area with the y-axis. Well, in that case, then we want it to be an x equals. Then our integral would be, what would this integral be then? From where to where? 0 to 2. And then it would be y minus 2 squared dy. Remember we said that means with respect to. So one of the things we'll have later on when we get into chapter 6, chapter 7, when we're actually doing application problems, kind of like in chapter 4, we use the derivative. We're going to be using the integral, and we'll have to set up these integrals. Now, a little word of optimism is these are usually a lot easier than chapter 4 ones. The application problems, a lot of times the conversation I have when people come to me at the end of term 3 and they're thinking about dropping, I say, geez, why drop now? You've been through the hardest part. Term 4 is the best term we have over here, and it's the easiest most of the time. Okay, no promises all the time. But we spend a lot of time. Spend a lot of time reviewing. 4 of our grades are the finals, and they're scaled. And you know what I mean. And the application problems, the integral problems, are usually not that bad to set up. But one of the things we have to decide sometimes in these integral problems, not right now, but later on, is are we going to do the area with respect to x, meaning vertically like this, or are we going to do the area with respect to y, meaning horizontal? And it's not that hard of a decision. But we get into integrals that are dx and dy. Now, the cool thing about this, and this is where I want to kind of bring the calculator, so somebody write this down, so I remember this. Write these 2 integrals down real quick. Who's writing? Connie, you writing? Write them down real quick. Write down that integral and write down that integral. Okay? So, how the low battery people coming? I may have to resend it. I don't know. Has it ever restarted? I may have to resend it.
I think that one was stayed up.
That's still red.
I think I'll get it right here.
Okay, I think it's charging, hers charging, so I think we're done. All right, well, so let me try. Okay, everybody else take your hats off. Everybody else take your hats off except Davey, and leave that one on, okay? Otherwise, it'll try to send it again. Okay, everybody got their hats off? Okay. Nope, low battery right now. Okay, so anyway, back to the calculator. So let's do a couple of these. Oops. Okay, there we go. All right, so I typed a couple of them in here already. Okay. All right, so I went ahead and typed in, this was last period, so I typed in this integral here. Now, where you do the integrals, you probably know, next to the 9, you go right here, here's your integral symbol, right here, if you want to do an integral. Now, we're not going to do much of that in the calculator in this first quiz in chapter 5. We'll be doing a lot of drawing pictures like you did today, drawing pictures, getting those integrals, and doing areas by geometry and various things, okay? But this is how you type in an integral. And so I went ahead and did this already for number 19. You know, okay? So if we go, okay. So if we go here and look at number 19, I went ahead and typed, well, that's number, here's 19. So I went ahead and typed that in, and sure enough, 9 pi over 2. Then we typed in number 20, and it gave us kind of an interesting thing. We were expected pi r squared over 2, but it gave us this. Well, it was because r is supposed to be positive. The calculator didn't know if r is positive or not. Think about what would happen if r is negative. If r is negative, then what's negative r? Positive, right? So when I type this in, then the calculator's thinking, well, if r is negative, then this would be going from positive to negative, which means backwards, right? And if it's backwards, what would the area be? Negative, right? It would be opposite, but in this case, it's above the x-axis, so it would actually be a negative area. So it was thinking, well, I can't have pi r squared over 2, because if r is negative and you square it, that's positive. This would be a positive answer. So what it is, it split the r up. It said, well, let's make one of the r's positive, and if r is negative, then this r will be negative, and then when these multiply together, that'll make a negative area. And if r is positive, it won't matter. If r is positive, these will both be positive, and then we'll get a positive area. Does that make sense? So that's why the calculator split that up. But when I did the vertical bar and told it that r is always positive, then it just said, oh, okay, well, that's pi r squared root of 2. Okay, so just, I think it's interesting when you look at what the calculator does and try to understand why it's doing it. Okay, so let's go down and let's type in those last two we did, Connor, the ones you just wrote down for us. So if I do the integral of the one that was given in with the y's, that was the integral from 0 to 2, and it was what? Parentheses y minus 2, oops, squared, and then it was dy. It tells me that area is 8/3. And it should be no surprise that if I type in the other version, which went 0 to 4, and then that was negative root x plus 2 with respect to x, that's also 8/3. Kind of cool. But it's just looking at that area in two different ways, but it's still the same piece of area. Okay, so we get the same answer. All right, so onward. Book problems. Questions? $56? Okay, good. I'm glad you guys asked about that because the other class didn't ask, and I said, hey, what about these? And then they're like, oh, yeah, I didn't get those. Well, yeah.
2.
Yeah.
2 right.
Is 2 the right answer to which one? 56, it is. Now, let's talk about this. They tell you the sine curve area from 0 to pi is 2. That's what they told you the direction. Okay? Well, okay, think about this. Basically, it tells you that one hump of the sine curve has an area of 2. So what do you suppose this is over here? It's got to be, because the sine curve has perfect symmetry. What about, well, so the answer to 56 is then cosine, which looks like this, from negative pi halves to pi halves, is one hump. Isn't one hump of the cosine curve the same as one hump of the sine curve? Because they're the same curve, just shifted, right? So yes, it's got to be 2. By things we know about odd and even functions and symmetry and stuff like that, it's got to be. Now, so you said 56 and you said 57, right? Now, I want to go back to 55. What about 55? Why pi plus 2, Cesar? I know the back of the book says pi plus 2. I always get a lot of people saying 1 plus 2, which is 3. Because you got 1 plus sine x.
The restraints are 0 to pi. So you would have the interval 0 to pi times 1.
Okay.
Pi.
All right. Because what does the plus 1 do here? But I guess I'm not getting where you're getting the 0 to pi and the plus 1.
Well,
You
it's
separate
the
Separate.
the integral. Oh, okay.
Is that what you did?
Yeah. So your integral it's 0 to pi. 0 to pi.
Oh, thank you.
Yeah.
So I say there's 2 ways to do this one. One is to separate it. Did anybody do something different than that? What is 1 plus sine x? What does that function look like? Isn't it the sine graph shifted up 1? So this would be 2 pi here. This would be pi right here. Right? So wouldn't we be talking about this area? Right? So, okay, so help me out. So how can I calculate that?
Do a square.
Yeah. That's 2. That's the 1 hump. And then what's this? It's pi wide. Okay, so lesson. Anytime we shift a graph up and we're doing area with the x-axis, what do we add? A rectangular strip of area that's as wide as our interval and however much we shift it up, right? So every time we shift up, we don't add 1 to the area. We add a 1 tall rectangle that's 1 by pi. That's where I thought you were going with that. Okay? So that's a way we would know that it's pi plus 2. But I like also what you said, what you guys said about splitting it up. Absolutely. That's what we learned yesterday. That when you have something like this, we can split it up. And so this we already know is 2, and then this would just be the graph of y equals 1 from 0 to pi, which would be that piece of area, right? So that's a good way to do it too. So I like both of those. So now, well, that takes us to number 57 then. 57 is the integral from 0 to pi halves of x plus cosine x. Well, what do? We split them up. The only really way to do this one is, it was a cosine or sine?
It was
Cosine. So really the only way to do this one is to split it up. So on this one you draw cosine from 0 to pi halves, which would be right here. Well, what is that?
1.
That's half a hump, so that's 1, right? And this is y equals x. I just want us to get real comfortable graphing these. And then 0 to pi halves, well, that would be, what would be the y value there?
1.
No,
Oh, okay.
right? It's y equals x, right? So if you go over to pi halves, you go up pi halves, right? So the y value is pi halves. So it's a triangle that's 1 half times pi halves times pi halves. So it's pi squared over 8. So this would be pi squared over 8 plus 1, right? So you got to split it, you got to draw it, you got to see what your shape is, then you got to do that area. Okay, that we need to be able to do. We need to be able to do these geometric shapes where we can draw a function and we can do it, and then we can split it apart. So here we had a piece, we don't really know how to find this area, they just had to tell us. So once they told us that one hump was 2, was an area of 2, then that gives us a lot of ammunition to do a lot of other stuff. And then these just make triangles or trapezoids or something like that, then we just calculate those areas by geometry. Okay, all right. What else?
I didn't
Yes,
know what
Spencer. 62. Cesar, what were you going to say?
I just didn't know what it was asking on part A of 71.
Okay, we'll get to 71. So, 62. Here's 62. Now, 62, I didn't want to make a big deal about this one, but I did want to talk about it just a little bit, so that's why I signed it. If you go back to page 307, it talks about bounding an area. So we have areas we don't know, like we don't know this area. Right now, we actually do know. They told us it's 2, okay, in the last problem. So that sign, now that may or may not be right. They just told us, assume for these problems it's 2, okay? But, so here's a piece of area. It's not a geometric shape. You can't really find it. Now, so we want to go from pi 6 to pi halves. Well, that one we actually can't do, right? Because that's just a piece of this. So that would be this piece right here. Now, even if we knew that whole thing was 2, we don't really know what that is. Okay, so the idea is, okay, if we don't know how to get the area, is there a way we could kind of trap it? Is there a way that we could find out the smallest it could be and the biggest it could be? And we could use minimums and maximums. So that's what the little theorem on page 307 is about. They call little m and big M for the minimum and the maximum. So what we can do is in this interval, find the lowest point, which would be there. Okay? So we take that lowest point and we say, what if the graph stayed there the whole time? Right? Because that's the lowest point, right? It's the minimum. So what if it stayed there the whole time? Well, we'd have this area, right? And then let's find the maximum, which is here. And let's pretend the curve was there the whole time. Because that would give us rectangles, right? Don't we know that the area has to be somewhere between them? We know the area has to be somewhere between them. Okay? So the littlest area would be the blue. So let's calculate that rectangle. So what would be the height of that blue rectangle?
Sine pi 6.
It'd be the sine of pi over 6. 1/2. So that's a height of 1/2. And what's the width of this rectangle? What's that width? It'd be pi halves minus pi 6, which would be 3 pi 6 minus pi 6, which would be 2 pi 6, which is pi thirds. Right? So doesn't that blue area have to be pi 6? And we know that the area has to be equal or greater than that. Because if the function stays at the minimum the whole time, it'll have that area. But if it's bigger than that, anywhere in there, the area will actually be more. So that's where that number comes from. Likewise, what's the biggest the area can be? What would be this triangle? How tall is it? 1. How wide is it? Same. Pi thirds. So, if the function stayed at its maximum the whole time, we'd have a rectangle area that would be that. But if it doesn't stay at its maximum the whole time, if it goes below that, then it's got to be less. So it's got to be below the min and the max rectangles. That's all that problem's about. It's kind of a common sense thing, but that's the idea. Okay, it kind of ties into derivative a little bit because that's how you define minimum and maximum and so forth. Okay, go to the next problem I wanted to talk about, which is 66. Then we'll talk about 71. Your work is your show. Your work is your show. Okay, all right. So on 66, I want to talk about that. That's an average value, okay? Because yesterday we talked about this. Whenever, just like in derivatives, whenever you hear average rate of change, what do you think? Slope between 2 points. Whenever you hear average value, whenever you read those terms, when you read average value, right away, boom, you think of this. Right? Just got to memorize that. When you hear average value of a function, the function goes in there, and then it's this formula right here. So when they said the average value of f between 0 and 1 is 2, and the average value of f between 1 and 3 is 4, what's the average value between 0 and 3? So as soon as I read all that, I'm writing this stuff down right here. Okay? That's the average value between 0 and 1. This is the average value between 1 and 3. This is what they want me to find. Well, this is easy. I got 1 here, multiply that over there. So I got the area from 0 to 1 is 2. Here, 3 minus 1 is 2. Multiply that over. The area from 0 to 1 is 2. The area from 1 to 3 is 8. What can I do with that? Add them together. Because we learned yesterday and in the video that the area from 0 to 1 plus the area from 1 to 3 is, remember we did that yesterday with this, we circled these. That's the area from 0 to 3. So this added to this makes the top. So the top is 10. And then that's just 3. And so there it goes. 10 thirds. So that's just putting together the things we learned about average value, what average value is, and this thing we learned about adding up chunks of area. Okay? Notation, stuff like that. All right, 71. Now this 71 is kind of foreshadowing a little bit stuff we're going to do later. Okay? You're going to have a lot of problems when we get to chapter 7 where they're going to describe a region. Okay, and so we need to be able to shade and identify that region. So in 71a, they said sketch the region bounded by these two curves and the line x equals 0. So I went ahead and graphed them. So here's one of them, y equals x plus 6. Here's the other one, y equals x cubed. Okay, and x equals 0 would be the y-axis. So wouldn't it be, aren't they talking about this black area right here? Now what's different about that area?
It's not any shape.
Well, right. It's not a geometric shape. What else? It's not with the x-axis. It's not between the curve and the x-axis. We're used to doing this area down here, right? This area under here to the x-axis, not to the y-axis. Now, we could do that thing where we kind of flipped it with the y's like we saw in the packet. The problem is this piece up here wouldn't work there because this piece, if we were going horizontally, these pieces would go to the y-axis, but these pieces up here wouldn't. So this is a whole other branch of areas when you do it between curves. We're not going to get into that right now, but this foreshadows it a little bit. So in part B, they say express this area using integrals. How could we find this area? Using what we know about areas between the curve and the x-axis. I'll give you a hint. Don't we know how to find this red area? At least, couldn't we set up an integral for that red area?
Yeah.
What would it be?
0 to 2.
Integral 0 to 2. No. It wouldn't have anything to do with G. I'm not even sure which one's F and G. Just tell me. It doesn't have anything to do with the cubic. The red area. Now I'm talking about saying the red area is what I'm talking about. The red area would be the integral from 0 to 2 of x plus 6 dx. But that's not the black area. How can we get the black area? Because the area of the cubic would be the green, right? So could we do the red area? We're used to doing that, under the line, down to the x-axis, and then under the cubic, down to the x-axis, and then subtract it. So this would be 0 to 2 x cubed dx, right? That would give me the black area. That's what they wanted in part B. Now, if you look in the back of the book, I think they put these together then. We just talked back here about splitting these apart, right? Right here, we talked about how you split them apart. What makes sense if you split them apart, you can put them back together, right? So I could then make this one integral, which would be x plus 6 minus x cubed dx, right? That would make sense that I could do that. Right? And we could type that in our calculator, we could see what that actually is. But okay, so that's just a little foreshadowing of some stuff we're going to do with these intervals. Okay, get your notes out. Okay, put that away and let's talk about this next thing here. All right, now you guys. One of them's going. Davey, do you get a message on yours? I think scissors is better. We'll give it a try. All right, what we're going to do is we're first going to remember, one of the things you're going to notice is how we kind of connect, how some things are similar and how we introduce area and how we learn about area in much the same way we did rates of change, okay? One of the things you might remember we did back when, you don't have to write this page down probably, the next one maybe we will, but remember when I gave you the sine curve and we were talking about slope being the slope between 2 points, and we said, okay, this is our F graph right here. Let's pick some points and let's do the slope. So on the sine curve, we calculated the slope right there. Remember what it was?
1.
It was 1. And then we went in a little farther. We said, let's go to like pi 6. So let's go in a little bit farther and let's calculate the slope. And it was a little bit less. It was like 0.866. Okay, and then we said, let's go to pi fourths, which is in a little farther, and the slope's getting less, and it was like 0.707, right? We picked 2 points really close together. We did the slopes, remember that? And then we said, let's go a little farther in. Let's go to pi thirds, which is about here, and we did that. That was 1/2. And then let's go up to pi, and of course that's easy. The slope is 0. And then we said, let's plot those. And so we go 0, 1, then we go into pi 6. We got 0.866. We got 0.707. Then we got 0.5. Then we got 0. We plot it. What did we get? And remember how cool that was? We're like, oh my God, you're kidding me. The cosine y values are the slopes of the sine curve. And that's exactly right. And we gave that a name, and we said, let's call that the slope function. And we said, let's denote it with a little prime symbol. We said it's going to be f prime, and that's going to be the slope function. And that's what it is. And that's how we started with f prime. We said it's the area, it's the, not area, it's the slope of f, right? It's a plotting of the slope. So if we look at the f prime graph, we know those y values are the slopes of the f graph, right? And we created the chart, and we had all those connections between f and f prime, right? Increasing, decreasing, concave up, all that. Okay. We're going to do something very similar. We're going to create a function instead of called the slope function. This you might write down. We're going to call it the area function. Now, first problem is, harder. But that hasn't changed. That's just an ongoing problem. The problem is, it's easy to do the slope at a point, right? So I can make a table for the slope function. I have an x input, and I want the slope at that x coordinate, and then that'd be my log. We don't do slope, we don't do area at an x value, right? We do area where? over an interval from A to B, right? So we can't say do the area at 2, do the area at 3, right? Well, we can if we do it this way. If we say, let's just fix our left edge. Let's just take the left edge at some constant and we're not going to move it. And let's let our variable then be the right edge. So we're going to put the x up there. So we'll have numbers down here, like this could be a 2 or a 0 or a 1 or a -3 or whatever. And we're going to put x as our right edge. Now we're going to call this function capital A for area. And the input, of course, is going to be x. Right? So this x in here is the same as that x up there. Okay? Now this is going to be the area under some f graph. So we're going to have some f graph over here. Right? Da-da-da-da-da. And here's going to be A. And over here is going to be x. And we're going to be talking about this area right here. Now we got a problem here in the sense that we got another problem. And that is we can't call that function inside there. It's called the integrand. We can't call the integrand f of x. Why not? Why can't I use x in here?
X is changing.
Well, because we're already using x for something else. We're using x to be this right edge, so we can't call this axis our x-axis. So I'll use t. We could use t, we could use u, we could use German shorthand, it doesn't matter. We just can't use x. We're using x as our right edge of our interval. We can't use x as the input of our function, of our little f function. It's the input of our area function. And that's what we care about. We care about this. This doesn't matter in there. It just can't be the same as that right edge. All right? So now, think about it. Every time we move to a new right edge, we're going to get an area. We could plot those, right? So I got a right edge here, I'm going to have a certain area. I have a right edge here, I have another area. Right edge over here, I have another area. Matter of fact, I can show you that here on this. Oh, wait, don't look. Everybody close your eyes. Okay, all right. So if so my left edge, so here I got a little f graph, it's this line. I got a little f graph, it's a line, right? And here's my yellow area, and x is my right edge. So x is at 10.45 right now, and it's giving me an area of this. And so if I slide this over to here, I got a new area, right? So I have another ordered pair. And I move it, I got another ordered pair, and I come back here, it's smaller. So here's an area. So I'd have an ordered pair of 4 and 1.7, right? And, oops, it's bad. Okay, there we go. And so I can move this around. And what would my area be over here, positive or negative?
Negative.
Whoa, whoa, whoa.
Awesome.
It's the integral, remember, from A to x. A to x is backwards, so that area below the x-axis is actually positive. So this is positive area, 15, right? Now, watch what happens when I come this way. What's happening to that area? It's going down. Why? Because I'm losing yellow area. And the yellow area we said is positive. So I'm losing yellow area. Now when I get here, what's my area from 0 to 0? Oh yeah, what's the area from 2 to 2? 0. What's the area from 3 to 3? 0, right? Okay, so I keep going here. Now I'm gaining positive area again, so my area is going back up, right? Now you might have noticed this little dot. What's this dot? It's these coordinates, right? This is 7.45 and 5.2. So right now we're at 5.29. So this point is just plotting these 2 points like I had in this table right here. Okay? So it's plotting the area function for me. Okay. So you can just see, right? You can just see that being plotted. So you can imagine that as its own function. Right? All right, everybody good with that? Any thoughts? Nope. Okay, never mind. Forget I asked. Okay, now, we don't want to do that. So, next thing, calculate. All right.
Finish.
Yep, okay. So, okay, Davey, we're going to try one more time. Take the hat off, Cesar.
Oh.
Got it?
Yep.
Whew. Let's go. good message? Okay. All right. So, everybody else, oh, gosh. God, we can't put the hats on yet. All right. So here's what we're going to do. Okay, what time is it? Okay, all right, we got time. We got time. All right, why does it say two are connected? Oh, because it says are just unconnected. Okay, we'll just sit here and watch.
Really riveting.
Okay, if you're watching the video, I'm going to pause it right now. Okay, you should be getting a document. Go ahead and open it up. Yeah. Intro to the fundamental theorem. Yep, that's it.
Fundamental theorem. What's it called?
Huh?
Is it called fundamental theorem?
Colin's a presenter. All right. All right. Colin's a presenter and Faith is a recorder. All right. So. All right. So. All right. Yeah. Go right back there. That's perfect. Okay. You're going to be recorded. All right. Now. And by recording, I mean writing. Now. So back to. So we were doing this. We had this. We were plotting the areas at these different right edges. Now, the thing you might want to pay attention to, and probably none of you noticed this, so I'll just say it. But you got this y equals x kind of line. That's not exactly what it is, but you got a line. And then the area seems to be this kind of curvy, kind of, I don't know, almost a U shape, kind of kind of this curvy U-shaped kind of whatever, who knows what kind of thing. All right, so Colin, go to the next page. Everybody else can follow along here. This would be great on yours. So now we're going to look at one similar, but we're going to start with a constant. We're going to start with just y equals 1.5, horizontal line. Okay, so go to the next page, Colin. And, all right, scroll back, grab that X and go back one. And then here's where I want you to write these down, Faith. We're going to grab these areas. If Colin, oh, did I pick a bad presenter? Yeah, looks like it. Oh, that's awful. Come on. There you go. All right, so that area is 1.5. That surprises 1.5 by 1. Write that down. Okay, then go over 1. And now the area is 3. That surprises. Go ahead, go another one. And now the area is 4.5, okay, and then the area is 6. Okay, good. Go to the next page. Okay, so if x equals 0, what's the area? So the area from 0 to 0 is 0 because there's no width, so you can't have any area. Every time we move over 1, how much area did we gain? 1.5. Makes sense. We gained a rectangle of area, 1.5 tall and 1 wide every time. Okay, so go ahead to the next page. Let's fill in the y column, Colin. And so, Faith, what did we have at 1? 1.5? Yeah. Right? That was our area, 1.5. What was the next one? 3. Next one? 4.5. These are easy. It's going to get harder next time. 4.5, 6. And we didn't do it, but it'd be 7.5. And sure enough, it looks like we get a line that has a slope of 1.5. Okay, go to the next page, Colin. Okay, now we're going to take a function that is a, it says what if you changed it from 1.5 to 0.5?
The area is proportional.
Yeah, so the area, if we plotted the points, would be what? A line, but it would only have a slope of 1/2, because every time we go over 1, we gain 0.5 area. Okay, next page. Okay, now we're going to change it to a graph of a line instead of a horizontal line. It'll be a diagonal line. Now notice it's t over 2 or 1/2 t, but really just think of it as 1/2 x. Why did we have to put a t there?
Because we're already using x.
Because we're already using x for our right edge of our area, so we got to use something else here. But when I see it in there, I just think of that as 1/2 x. I think of that as the equation 1/2 x. But 1/2 t, whatever, same thing. Okay, so this is 1/2 x, so it's going to be a line. So go to the next page. Okay, so get ready to record. So scroll back to 1. Oh, he's getting good. Okay, so a little more farther. There it is. Okay, 0.25 is our area. Okay, we got a little triangle there. Now scroll. And now it went up to 1, so we gained 0.75. Okay, now go again. 2.25. Now we gained 1.25. How come? What's happening? It's going up. Yeah, so what? Because what's happening? Every time we move over 1, we pick up new area, right? What kind of a new area? Positive area. And before we were picking up rectangular chunks, right? Here we're picking up trapezoidal chunks and bigger chunks, right? Every time we move over 1, I'm sorry to be so technical, but every time we move over 1, we're getting a bigger and bigger chunk of area that we're adding on, right? Okay, keep going. So 2.25, next one over, 4, next one over, 6.25. So this is a lot like the one I was doing, right? We had that line, and as I drug it, I was picking up bigger and bigger chunks of area, right? And so it was giving us this weird kind of U-shaped curvy thing. All right, now go to the next page, Tom. Okay, so again, if x is 0 and area is 0, 0, it should be 0. Why doesn't it increase by the same amount? We just said because bigger and bigger chunks. Okay, go to the next page. Let's fill this in. So we had what? 0.25. 1, 2.25, 4, 6.25. And so sure enough, it's kind of going up, not in a linear fashion, but more in a kind of curvy, almost U-shaped kind of fashion. Okay, next page. Okay, is the graph linear? No, it seems to be curvy, almost U-shaped. Okay, go to the next page. Now let's take a quadratic, a parabola, and let's look at that. And we're going to pay attention to that area, but not only that, this curve's going to actually go down below the x-axis, so we'll get into some negative, kind of check out max min points. Okay, go to the next page. Okay, so go back. Okay, we're over there at 1, so write that down, 1.76. Actually, I'm not sure we're going to need to write that down, but do it anyway, just in case, I think. So now that's positive area, right, from 0 to 1. Okay, go. Scroll again, and 2.3, so it's getting bigger because we picked up some more area, but a smaller chunk that time. But we picked up some area. Okay, now go, oh, wow. It went down.
Wow.
Oh, we picked up, sorry, you got to fake it, do it. Okay, so you picked up a chunk of negative area, so it went down. Picked up another chunk of negative area, so it went down again. Keep going. Picked up another chunk and a bigger chunk of negative area. So now our total area is actually negative. Okay, go again.
So the area functions.
Picked up a bigger chunk of negative area, so it's really going down. Okay, go one more time. Whoa, stop right there. Okay, now, so I mean, think about it, man. This area graph is going down, but we're picking up bigger, bigger chunks, so it's really going down, right? Like crazy, right? It's really going down. Okay, well, so now go over one more. Go over one more, and oh wait. We picked up a negative. It's still going down, but what happened?
Picked up less of a negative chunk.
Picked up. Go again. Picked up a smaller chunk. So it's almost as if that area graph's going down and steeper, 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 and then it kind of hits some spot. I don't know, a point, call it maybe, where it just and it keeps going down, and then but it's kind of almost turning and curving almost a different direction, kind of. At that kind of special kind of place right there. And that kind of corresponded to here, right? Yeah. Right to there. Okay. And so, and you know what we didn't talk about is kind of back here, it kind of peaked. I mean, that area started, it was going up, and then it's kind of started going down right when this kind of stuff happened. Okay. So So, okay, so go to the next screen, Colin. Okay, so.
Did you record this, Clark?
I am, yeah. At what value of x does the integral value begin to decrease? So we were just talking about that, is right when it crossed the x-axis right there, which maybe is a coincidence, I don't know. What are all values of x where the integral, the area is decreasing? So we're talking about that, is decreasing, then starts increasing. What's true? Oh, that's probably too hard for us. What's the smallest value of the integral? It looked like it was going to go down and kind of peak, but I don't know. So, okay, go to the next page. Is there a connection between the location of the minimum area and the sign change? Scroll back. Yeah, we didn't get that far, did we? Okay, yeah. So if we keep going, so it's going down, 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 but we said it's kind of flattening, keep going. And it's still going down. We're picking up littler chunks of negative. And then all of a sudden, well, now what?
All right, going back up.
Okay, I know. You guys know what's going on. What's going on?
I don't know.
What's going on?
This is This is new information.
Right? If we had to put A on here somewhere, where would it go? Isn't it there?
No, yeah.
What?
Well, I don't know. What do you tell me? Is it? Well, you said it, Trey. What is it? Isn't it the antiderivative? When we had an x, when f was an x line like that, what was a? An x squared? A parabola? Wasn't it? I think it was. I mean, right? And when it was a constant, when little f was 1.5, what was area? Wasn't it a line with 1.5 slope? It sure seemed to be. Now, that seems pretty crazy, right? I mean, remember we talked about slope, and what I always thought was so amazing about f of x plus h minus f of x all over h is just a slope formula, and that's how x squared became 2x and x cubed became 3x squared. Remember that? It was kind of like, wow, how did that come from? It came from slope. What we just talked about here is area. If we just talked about area, looked at the little f graph, it sure felt like that was the f prime graph, didn't it? I mean, where the little f graph went from negative to positive, the big A seemed to have a minimum, and vice versa. When it went, did I say positive to negative? Positive to negative would be a local maximum, it seemed to be. That minimum down there on little f seemed to be the inflection point, right? I mean, it sure felt like chart stuff. Tell you what, let's do. Let's do this problem right here, and let's see what happens. Okay, so let's take this, so you can write this down. This would be good to write down. So notice that I've actually put something down on that calculator document. We had a 0 down there. I'm going to put a 2 down there as my left edge. Remember, it doesn't matter. It just has to be locked in. The left edge just has to be locked in. Okay? So, as if what we've discovered today isn't cool enough, I mean, really, the area seems to be, if you take and make area a function under the little f graph, its values seem to create or be the antiderivative, amazingly enough. But let's actually take it as an equation and let's look at it. So let's graph this function right here. Now notice up here I've called it f of x, and we said you can't use x because you're using x over here. Why is it okay to use x here? Yeah, it's not inside here, right? Once we put it inside here, though, I can't say f of x. Does that make sense? So in here, it won't be x plus 3, it'll be t plus 3. But it's the same thing, right? But I just can't use x for two different things in the same line, right? Up here, I can say let f of x be x plus 3. I could have said let f of German short hair be German short hair plus 3. Let f of u equal u plus 3, right? Whatever, okay? So let's go ahead and graph it. Let's get a grid in here. You guys can just draw it. If you want to draw this, you can just draw just a simple, just a line. It doesn't matter. It doesn't have to be real fancy. But I'll go ahead and actually draw x plus 3, slope of 1. I'll tell you what, are you guys getting weird calls? I'm getting these calls from
Florida. I just got one a second ago from Los Angeles.
Port Mugu, Nawak, California. And I got one an hour ago from Blacksburg, South.
Yeah.
What's going on?
I heard that it was something like, they like wait for you to say something, and then like they can use like your voice, and like.
I heard that on, where they said, what do? They ask you, can you hear me? I heard they say, can you hear me? Or can you understand me, or can you hear me? And if you say yes, then they take that recording of you saying yes, and then use it like you've signed up for some credit card, or you've signed up for
they'll like take you for it.
Something like that, where they can prove it's your voice saying yes, or something like that. Yeah, I did hear something like that too.
Texas and Garden City, New York,
Yeah.
Croatia?
Croatia, really. See, so I haven't answered any of them, so
I got 9 in one day.
yeah, I keep getting them too. Okay, anyway, back to this. So we got y equals, okay, y equals x plus 3, but technically this is t plus 3 when we put it on here, so that's the t-axis. Okay, it's one of those things that can get a little confusing, but it shouldn't really be that confusing. It's just that we use x up here. Now, we don't always use x up here. Sometimes they'll call this, I don't like to do it because then it's like almost they're trying to confuse you. But if we use t here, we would use t here. These have to be the same, and then this in here has to be something different. So if I use t here and here, I'd probably use x in here, right? It just, as long as they're good. Usually, though, it's the x's are here. In there, you see t's. All right, anyway. Our area function, let's make it red. Our area function is going to be the area from 2 to x. Now, I'm going to go ahead and rewrite this because I don't like putting just f in there. I like to actually put what the function is. So what is the function to the left? T plus 3 dt is what I'll put here. Now, remember, when I look at that, I think to myself, it's really x plus 3, right? I got to put t plus 3 there. Okay, so here it is. Here's my blue line, x plus 3, t plus 3, whatever. Now my red graph is going to, or my red is going to be that area. So it's the area from 2 to x. Now I'll just put the x over here somewhere. It doesn't have to be. Couldn't I want you to think of this x too, like in that other thing where I was dragging it. I want you to think of that x as draggable, right? So could I drag that x so it's over on the left side of the 2?
Yep.
Sure. But then it would be backwards, and then it just gets more confusing. It works, it's fine, everything will be great, but it's just easier to see if we just keep the x over on the right. We call it the right edge, even though it could move over and be the left edge, but then it's backwards. It's still the right edge. Okay, so it's still 2 to x when we do it. Okay, now, what shape is that? It's a trapezoid. Well, we can find the area of a trapezoid, so our a of x should just be the area of this trapezoid. So the area of a trapezoid is 1/2 the 2 bases. Now, is this base going to change right here?
No.
No, that's always going to be 5. Okay. Plus, and then what's this base over here?
X plus 3.
Okay, very good. Because its x coordinate is x, so you plug an x into t plus 3, you get x plus 3. Very good. This y value right here is going to be not t plus 3, right? It's an x plugged into the function. So you plug an x into little f, it's x plus 3. Okay? So that's very good. So that's that. And then times my height of my trapezoid, which is this down here. That's x minus 2. So let's go ahead and work out the algebra of that. This would be x plus 8. This would be x minus 2. This would be 1/2. That would be x squared. 8 minus 2 is 6x minus 16. We go ahead and distribute. We get 1/2 x squared plus 3x minus 8. That's my a of x. I'll go to a new page here in a minute. Right? Just simple trapezoid is all I did there. Right? I drew my picture just like you did on your homework today. Gave you an integral. It's different though, as my right edge was x, not a number. So it's a little different. And so I end up with my area equation being that. Now, what do we think? Still think an antiderivative?
Yeah.
Okay. If we go to the next page, and let's.
Wouldn't it like a straight line be like an absolute value? Because if it's like 2 to x, but then if x goes negative, isn't it still positive? So wouldn't it be like a...
No, but remember, if you go backwards, if you draw a graph backwards, and it's still positive, if you're drawing backwards and it's decreasing, actually that's an increasing graph, right, if you're drawing backwards. I mean, no, it's not going to be absolute value. Well, I'll show you here in a second. Because it depends what your other areas were. It just means that chunk there will be positive, but it's added on to whatever your other one was, right? So if you had more negative, it still could be negative, right? Okay, so let's see what we just came up with. We just said that if we have this area function, which is 2 to the x, t plus 3 dt, right? Where this function in here is little f, right? This is little f right there, okay? We just discovered that that would be 1/2 x squared plus 3x, what was it? Minus 8. Now look at those two. Is it antiderivative? Certainly it's antiderivative, right? The derivative of this is x plus 3, and this would go away. Okay? It is definitely antiderivative. Now what about that minus 8? That's that plus c thing. So let's take this one step further then. If we really believe, if we really are convinced now that when I have an area function, that it is the antiderivative of whatever function's in here, would I really need to go through this whole trapezoid business? Not really. What I could do is what's in the blue here. I could say, hey, if I'm going to do this area function, now I'm going to use x's instead of t's, right? Because as long as it's not inside there, I can use x's, right? So my area function, without even doing that trapezoid business, I could have just looked at this and said, hey, that's 1/2 x squared plus 3x plus c. But now how do I get the c? Well, we need, you guys said it, an initial condition. Is there any way, is there some value that I know on that area function? Don't I know a of 2? What's a of 2? No.
Oh, 0.
F of 2 would be 5. A of 2 means put a 2 here, which means put a 2 here, which means I'm doing the area from 2 to 2. No matter what my left edge is, won't I always know one area value? I'll always know the one where it's 0. If this would have been a 3 here, then the area from 3 to 3 is 0. So I know that in this area function, I know a of 2 is 0. Remember in the calculator thing Colin's doing, it kept saying this, when x is 0, what's the area? Oh, it's 0. I know a of 2 is 0. So you're telling me I could come over here and put a 2 in for x? This is going to, I'm going to freak out.
2 plus 6.
Oh my goodness.
Oh my goodness. It's like magic.
Been doing this like 20 years. I still get goosebumps. All right, what just happened? Look at that. Right? So, last idea. What did we just figure out about the plus c? Well, yeah. Well, not only that, but if I take weirder functions and put them in here, and then I draw a picture, am I always going to have some geometric shape I can do? No. So we're going to go through this some more tomorrow, and you're going to do some, not on tomorrow's homework, but the next day's homework. So you're going to actually do some of this and recreate some of this. But in the big picture, that's more about the concept and more about this antiderivative idea. In practice, what's going to happen is we're going to do it more with antiderivative, right? Which, of course, is why coming down the road we have the gateway test on antiderivatives, because well, like Joe said, it's way easier to just go do the antiderivative than have to go through that whole area business. But you got to know how to do antiderivatives, right? So, but anyway, don't worry about it. But anyway, back to what I said. What determined, or where did that plus c come from?
The x-intercept.
I'm not quite sure you're there. What is it that made there be a minus 8 at the end of that?
When you make the area actually equal.
So what would make me get a different value over here? The left edge. So I guess what I'm saying is, if I change this left edge, is it going to change this function?
Yes. Well, just the
Just the plus C, right? It'll still be, so I could, all day long, I could sit here and put different left edges on this area function, and every single time where I still get 1/2 x squared plus 3x, because it's still going to be the antiderivative of that. Okay, and I think we could probably see that best if we go back to this guy right here. And I was telling you, and we were kind of joking about this curvy kind of thing. But it's I know. That's why I waited. I didn't want to blow anybody's mind right away. But no. So yeah. So this is this area function, and so this kind of gets back to your absolute value thing you were talking about. I mean, when we go here,
On that. Is
yeah,
it on a straight line, is it absolute
a
value?
horizontal line.
Like a horizontal line.
What
Is
was
it not?
well?
It'd be a constant slope, wouldn't it?
Well, yeah, but
Here, okay, I can't make one where I slide real quick, but let's just say we had this right here. And let's say we had our left edge here and our right edge here, okay? So this would be a positive area. So I don't know what it is. So let me plot that. So let's say that would be an area maybe up here, right? And then as I slide this way, what would happen?
it's close to 0.
I would lose, this is positive area right now, right? So I would lose positive area. So this would be coming down, down, down until the x got to where? Right there. Then I'd have 0 area, right? Now, once my x slid over to here and I started picking up this area, this area is now negative.
No, because you're going back.
I'm going backwards, but it's above the x-axis.
Oh.
So it's negative. So now I'd be picking up negative area. So what would this do? It would just keep going, right? Now, here's where we got to be careful. This is actually in today's homework. You're going to get into this a little bit, where we got to be a little careful with increasing and decreasing. Because when you go backwards, these red dots are what? Increasing or decreasing? The red dots are increasing. Because whenever we talk about increasing, we always talk about going from left to right, right? But when I was drawing them, what did it feel like the red dots were doing? Right? It felt like decreasing, but they weren't. It was because I was going backwards, right? So when you think of this sliding, we got area up here that's positive. As I slide this, the yellow goes away, right? Well, here, let's just do this. So as I slide this, I like to say I'm losing positive area. Well, what's that mean? If you lose positive area, it means it's decreasing. Now remember, I'm going backwards though. So even though it feels like it's decreasing, it's really, the graph's really increasing, right? Because increasing, we always are talking this direction. Okay. But as I slide this, I'm losing positive area. So that dot is going down. Once I get to here, I start picking up. No.
You're losing negative.
See, because this now goes below. See, this is negative area. No, I'm not losing. Look at the yellow. The yellow's growing. Here I'm losing positive area, right? Because the yellow is going away. So I'm losing area. But right here, once I pass that left edge, now I'm gaining yellow. But what kind of area is it? It's now positive area. Right? Because it's below, which means negative, but I'm going backwards, so it's positive. So I'm now gaining positive area. So what's the dot doing? Going back up.
Double negatives.
But, right, okay, so you're going to have to get that clear in your mind when we start doing chart stuff. Okay, but wait. This is cool. Stop. Wait. So, there is more. One last thing. What did we say? We said the left edge determines what? The C value.
Does it just?
Are you ready?
Yeah, I'm ready.
You sure?
Does it just slide?
Oh.
That's not okay.
It doesn't just slide.
No. What is the plus C? What's the plus C?
The vertical shift.
It's the vertical shift. The plus C is just the vertical shift.
Is it equal to
Good buddy, fair enough.
the horizontal movement? Oh,
No.
it never
No.
goes up though.
It depends, but it's that. Well, right. Now, okay, time out. You said how come there's a point where it never goes, right? It hits here and goes back down. Well, why is that? Well, because there will never, if this went all the way up here, right? then the area would never cross the x-axis, and that would tell you the area is never zero. But doesn't the area have to be zero? At
A equals A.
right, at A equals A, right? I mean, there has to be a time when the area is zero. Right? There has to be a time when the area is zero. Now, there's actually two times, a lot of the time, the area is zero. The area is zero here because those two cancel out, right? If the x gets to here, there's another time the area is zero, right? So, you can get, I mean, so how, it's not going to be the plus c, the c is not going to be, go through all the values, negative infinity to infinity, right? But don't worry about it, that's not good. But that's pretty cool. I mean, that just shows you the effect changing the left edge. It just affects the plus c. Vertical shape. Okay, so for our homework. Oh, really? After a day like that, and you still, you should be busting out of here saying, I'm skipping that senior meeting. I can't wait to do my homework. Even it, Trey, if you have to fake it, right? Even if you have to fake it. I don't, oh.
Get us time for meeting today.
It's like that local scholarship thing, right? Don't you have to go to one of them? It's today, tomorrow, or Thursday. All right. Here's what we're doing. Now, I'm going off the track a little bit on the assignment here because we had 2 days here for 5.2. We're actually going to do 3. And then kind of include this a little bit, because here's why. Because we got a short period tomorrow, so we're going to shorten it up here a little bit. Then we're going to do some more 5.2 tomorrow. Then Thursday we're going to get into 5.3.
Okay.
And then Monday, so we don't have school Friday. Then Monday, tie it all together, kind of finish up, review, whatever. And then Tuesday's our next quiz. So Tuesday is this quiz. All right. So on the homework, now look at this. Now I get made fun of every year, so I'm just going to show it to everybody. 2, 3 through 8, 9 through 14. Now I did that because those are actual sections of problems that are related. That's why I did it. But anyway, we're actually only going to do 2 through 11. That's it. Now, yeah, see, you guys are so quick to go. Now wait, time out. So, on that homework page, you're not going to have to go through that area picture and all that stuff we did on that. Tomorrow we'll get into that some more. But basically our big takeaway from today was that the big A function is the antiderivative of little f. Kind of like big F is the antiderivative, right? Big A is the antiderivative. So what they're going to do is they're going to give you a little f graph, I think, and they're going to ask you questions about big A. Now, a lot of those questions will just be chart-related stuff, right? Because all those relationships we had in the chart now will apply to the area function. So it's mostly going to be those kind of things, okay? So that part of it should be easy, but I want you thinking in terms of areas and getting used to the notation. So that's why I didn't give you a whole lot of them yet today. But spend time on them, thinking about them, making sure you're comfortable with the notation. First two targets.
Mr. Clark, I'll be gone tomorrow. I didn't even know that. So are we doing it?
Really?
I don't know. I didn't even know.
Yeah, just one. It'll be at the end.
Yeah. Okay.